All right, welcome back to Calculus 2. We are going through our test review here. This is problem number 3C. So this is determine the exact area of the surface revolution obtained by rotating the curve, the square root of 1 plus e to the x, about the x-axis between 0 and 5. So let's go ahead and have a look at that. So over here, we're going to just write down the thing. We're going to say, okay, this is y equals the square root of 1 plus e to the x between x equals 0, x equals 5. So we're looking for a surface area of revolution. So we still want a surface area of revolution. We're still revolving around the x-axis, so like that. We're taking little slices here. We're going to go ahead and rotate it. So again, we have two different formulas we could choose from. We have surface area equals 2 pi integral of f of x times ds, or 2 pi integral of y ds. Okay, so we're taking this little spot of ds here and rotate it around the axis. I still need my radius, which is going to be this guy here. You can either say this is y, or you could say it's f of x. Since this problem does not scream to me, please use y's, and since it seems to be set up as x's, we'll go ahead and leave our f of x. So our ds, we're going to say ds is equal to the square root of 1 plus dy by dx, okay, squared dx. Okay, and again, you can go either way, but I think in this case, it's better off to go with the x's rather than the y's. Okay, let's sort this out because this is going to be kind of a pain. So let's set up the integral here. So we're going to have 2 pi integral 0 to 5, I believe, of y, or f of x, which was the square root of e to the x plus 1, times 1 plus dy by dx squared dx. Now, let's go ahead and deal with my dy by dx. Okay, so we're going to write down y. Okay, first, and we'll deal with that. So we have y is equal to, we'll make this a calculus problem rather than an algebra problem, e to the x to the 1/2 power. And it will say that y prime dy by dx is equal to 1/2, 1 plus e to the x raised to the negative 1/2, just doing a power rule, times the chain e to the x. Let's go ahead and clean that up a little bit. And we're going to have, this is going to be e to the x over 2 square roots of 1 plus e to the x, like so. Okay, we're going to go ahead and square this thing. So we're going to get, this is e to the 2x divided by 4, 2 squared is 4, times 1 plus e to the x. And now we have to add 1 to this business. Okay, but instead of adding just 1, what we're going to do is get common denominators here. So I've got e to the 2x over 4, 1 plus e to the x. Don't multiply out the denominator. We have 4, 1 plus e to the x over 4, 1 plus e to the x. So we're not going to multiply out the denominators, but we will multiply out the numerator. So I'm going to say this is equal to e to the 2x plus 4 e to the x plus 4. And this is all divided by 4, 1 plus e to the x. Now, this format here is something you could factor. If I had rewritten this, don't really take this as a substitution, just as a way of thinking about it. So if let t equals e to the x, we'd have t squared plus t, plus 4t rather, plus 4. In that format, I think you could say hey, we could factor that. Let's do that now. So this is going to be e to the x plus 2 squared. Okay, and what we're going to have on the bottom is 4, 1 plus e to the x. Now, did you forget about the outside yet? Because we still have a 1 plus e to the x to the 1/2 power sitting outside. So really what we have here is, here's my 2 pi, here's my f of x. So this is the square root 1 plus e to the x square rooted times a big square root of e to the x plus 2 squared over 1 plus e to the x. And there's a 4 in there. I'm going to go ahead and move that 4 to the outside and call this a 1/2. So it's multiplied by the whole thing. Conveniently, here's some 2's to cancel. And what we have here is the pi integral of the square root of 1 plus e to the x times, and this is still inside the square root. Since these are both square rooted, we can put these together. So this is going to be an e to the x plus 2 squared over 1 plus e to the x, and this is all under one big square root here. Okay, I'll put in the x at the end here. So some stuff cancels. Okay, and we can certainly take advantage of the square root and the squared here. So we're just going to end up with a pi 0 to 5, right? E to the x plus 2 dx, and that's probably the kind of integral that you'd like to see in Calc 1. So we end up with pi e to the x plus 2x as x goes from 0 to 5. Let's go ahead and plug that in. We've got pi, we've got e to the fifth power, which is a huge number, plus 5 times 2 is 10, minus, and this is evaluated at x equals 2, equals 5. We're going to subtract at x equals 0 here. E to the 0 is just 1, and 2 times 0 is 0, so we don't have to worry about that. Let's clean this up a little bit. We have pi times e to the fifth, 10 minus 1 plus 9, and let's call that good. Okay, so that would be the exact value for that surface area of revolution. Again, this one was pretty straightforward. It's a little tricky in how you add the 1, but for the most part, most surface area problems tend to have this kind of pattern, tends to have this kind of rhythm to it. So try to remember, like, you're going to have to add that 1 somehow. Sometimes it's useful to like multiply the outside end. But way over here, if I wanted to go ahead and just distribute this to a 1, we could do that and push it in here, push it in there. Sometimes it's better off to add the 1 as common denominators. It really kind of depends. But if you try one way and it gets kind of stuck, try the other way, see if that happens, see if that's helpful. So anyway, thank you very much for tuning in to watch this. The best of luck with your tests, and I hope this helps somebody. Thank you and good night.